Yes.
In this function, why didn't we return anything?
Oh, so it actually returns it.
Even when we don't write it.
Yes, even though we don't write it, it returns it. Yeah, so if the function can be written in one horizontal line, then that's okay. You don't need return. It will return whatever the value is. But if you need to go and find the length, then you can't do it this way. It has to be in a bracket so that it is run as a chunk. Yes.
We're comparing the 9.99 something.
Yes.
Where is that coming from?
Okay, so remember we did this. This one. We used a P when we were talking about the survival. Yeah. So we took the quanta of 10 and then we found the probability that you use more than 10 minutes to do the exercise. So that probability was what? 0.135. Now, what we are doing now is that we've given you the probability. And then we want you to tell us what is the time the student will use to complete the exercise. Yeah. So it's like inverse of the other. Okay. Please, is everybody okay? I will fine. Were you able to do it? No. Okay. You okay?
Why we should be using one
If you have any issue, please let me know. Extension. That one they can't provide. Doreen is here. Oh, but there's a spare one here. Do you want to come and sit here and use it? You can come and sit here and then plug it in. Hey, my own, but I haven't. Okay, please, any question? So please, is everybody okay with what we are doing? Yes. You had a probability distribution. Now we're able to find density, which is, yes.
You're getting into the probability.
Okay, so we're able to find the probability that it exceeds, it is below, and then if you have the number, or you have the probability. Can you tell us the number that generated that probability? That's the quanta. Okay. Now, so we've seen Q, we've seen D, and we've seen P. What we are left with is what? R. Is everybody okay with this? Okay. So the R generates observations. So that's what I was saying yesterday. That if I want, let's say, to know the ages of students in the other class, I'll now have to stop whatever I'm teaching you and go and ask them and come back. By the time I come back, it's 8 and we have to go. Okay. But we can just check maybe from the registry, or maybe the department will have some statistics that, well, level 100 students, their range, their age ranges from, let's say, 16 to 20 at level 100. Then if we want we want to generate, let's say, the ages of 10 students, we can randomly sample from a distribution that has a range between what? 16 and 20. Quickly, and use it to do our work rather than go there and now go and seek permission from the lecturer and then randomly sample 10 people. By the time we finish, most of you are gone. Okay, so that's it. So that's the sort of thing. or you are an organization, you deal with insurance. So you want to know the claims. If you study them, the claims, you can fit a distribution to it. Once you know the distribution, it means you can generate claims randomly from it. That's the sort of thing we want to do. That's why we want to really understand that. So it means that in the claim scenario, if I want to go and do reinsurance treaty, which is that I go to, let's say, Ghana Re, and then I said, well, every premium that I take, I'll give you some percentage on it. Then if a claims comes and it is beyond this value, as an insurance company, I'll take, let's say, if the insurance treaty is 7,000, it means any value above 7,000 will go to the reinsurance company. Okay, so let's say somebody goes and crash a car, or there's an accident, fire accident, and you have a reinsurance which is set at, let's say, 7,000. Then the insurance company will bear the 7,000. The reinsurance company will bear the rest. So if it's 20,000, I only pay 7,000. The insurance company will pay. Sorry, the reinsurance will now take what? The difference of 13,000 to pay. Okay. So for me to be able to decide whether to pay that or not, I need to be able to check how many of my claims go beyond, or what is the proportion of claims that goes beyond 7,000. Okay, so if that probability is 1 out of 1,000, and then you go and they tell you that every premium that you take, they are going to take 5% or 10%, will you go for it? Maybe no. Because that's just 1 out of 1,000. Why should I be giving you 10% in whatever I take? And so all these are part of the things you need in making a decision. In whichever field you find yourself. Okay. Any question on this? All right. So now let's see how we will generate random variates. So how do we do so? Well, here we know of the exponential, right? It says RS. So all we need is just the number we require and then the rate. So what we are going to do is that we want to generate the 10 people. Let's say we want to generate 10 random times that it will take for students to complete the multivariate question. Okay, so what that means is that we will take what? 10. What is the rate? The rate was what? 1 over 5. So let's generate. I got this. So maybe I can name them times. And then I'll round it to, let's say, 1 time. So let's just dig it is equal to 0. So, okay. So I got 1. So the first person used 1 minute. The next person used 3 minutes. The next person used 6 minutes. The next person 1 minute. 8 minutes, 5 minutes, so 6 minutes. Then somebody used 16. Then somebody used almost, it won't be exactly 0 because this is exponential. But because I'm rounding it off, if it is 0.4, it will be what? 0. And so forth. So please generate your own and tell me. We won't get the same. Because this is random, yeah. So tell us what your sample is.
Mine is 5.
Okay.
So the 1, 2, 1, 4, 8, 2, 3.
Good. Yeah. So those are the time in minutes that the student. So you see, you don't need to now let them do the work itself. Because we knew the rate, we are now able to create copies that will represent what it, and that's what simulation is about. That we will mimic real life situation. Okay. Yes.
So if we are doing this to estimate the mean,
Yes.
and then we have to provide the rate also to do our simulation,
Yes.
what is the goal?
Well, as I'm saying, assuming I want to, okay. So remember the way we said how many the average is 5, right? But we know that it follows exponential. So because of that knowledge, we are able to create several copies of sample times. Okay. The only thing you need to realize is that the distribution takes the rate, not the mean. But we know the theoretical relationship between the mean and the rate. That's why we put 1/5 there. Yeah. Okay. Can we get some more? Who else? Your sample. You got 16, 0, 2, 2. You got the same. You did not use any set seed.
I had C from yesterday.
Well, okay, rerun it and let's see.
I had 4, 3, 7, 2, 2, 4, 1, 4.
Maybe you ran the seed with it today. No, I'm sure you ran it again. Did you run all your codes from this yesterday?
I have changed.
It has changed.
What is it?
Okay,
2,
send.
1, 4,
Okay,
8,
good.
2, 3, 20, 4, 5, 7.
Good. Okay. Please, is everybody okay? It has changed, okay. So, do you realize the difference between this and what we did yesterday on the Lotto numbers? Do you remember what we did? That was also random sampling. So that the Lotto one, we have the actual values and then we sample from it. This one, we have a structure for the data and then we generate the observations from that. Is everybody okay? All right, okay. So now, what we want to do is generate more. So let's do a histogram of this and see how it looks like. Or first of all, let's find the mean. The mean times. I got 4.95. What did you get?
4.927.
Okay, good. So now we are going to change the sample size to 100. Let's all follow what we are doing. So first of all, our sample size was 10. We found the mean. Oh, I need to create the histogram as well before. So this is what it looks like. Let's do the Palmer. So let me run this and then come and run my histogram again. So this is it. Times. So it looks big, but it's so small, so you don't really see the exponential one.
Do we have the main
because I don't want a title. Remember, the main is the title. So if you don't put main is equal to an empty set, you will see a histogram of times. But we don't want at the top. We don't need that. Okay. So please, then you go back, you change it to 100. So those are the times. The mean is now 4.67. The first one, I got 4.95, but now it's 4.67. My histogram, does this look like an exponential? So when I increase the sample size, you realize this is approaching an exponential curve. Okay. I can increase this to 1,000. I don't want to, I'll comment this one, otherwise all our, so don't display it again, but the mean is 4.81. Histogram is becoming a bit more exponential. I can even go to 10,000. And so forth. And you can move. But the more you get more sample, the more sample you have, the more you're able to show or display the actual distribution you're after. Any question? You remember the law of large numbers? Shall we move on? Okay. Now, so let's say I wanted to demonstrate something, but sometimes that's random sampling. Do you remember the law of large numbers? Let's say the weak law. You did it in the probability. Yes. So now what we are doing is to relate to all what you did. That's computing, statistical computing. You always go back. You need a theory to really understand whatever you are doing. If you remember that, it says that if we increase the sample size, our sample estimate now tends towards the parameter. Okay. Now, do you remember the mean time for this exercise? 5. Okay. So the expectation will be that if we take a smaller sample size, our mean should be far away from the actual one, but it should get closer to 5 as we increase the sample size. Okay. Now, if you look at what I did, I wasn't getting that. But that's also possible because we are doing random sampling. So it's possible that when you sample, most of them will be lower, even though they are many. And so forth. But on average, that's why when you are doing simulation, you don't do it for one instance. You do it multiple times so that it takes out all those outline generations from it. So let's go back again and do the same exercise. Generate the times, find the mean. So this one, you see, it's far off. Okay. So sometimes I can let you do this, then I ask you, what statistical principle are you demonstrating? You see, once we go to 10, it is getting closer to the 5, right? That's it. I increase it to 1,000. I expect to get more than 4.65. You see, it's now beyond it. But it's closer to 5 than the 4.65. Okay, then I get 10,000. You see, this is also closer. Yeah, so we expect that as you increase the sample size, we should get, and that's a weak law of large numbers. Okay. So this is a more reason why, let's say, if we are taking a sample, we take more sample because the statistical theory tells us that as we include more observation, whatever opinion we are getting from the people will represent what is in the population. So, for example, if you want to now determine who will win the next election, the ideal thing is to interview every registered voter. Right, and so forth. But there's not much time, the logistical constraints, and even locating all of them, costs and so forth. So you take sample. But you must take sample as large as you can. But of course, it comes from your pocket as well. So usually, budget will influence your sample size. And you should take note of this, because when you go back and you go for the graduation, and then we give you the gown, and you go back to your workplace, they are going to, oh, he has done statistics. We want to do this study. What is the sample size? That's what that question they will always ask you. Yeah, so make sure you have all this at the back. Okay, let's try this same exercise, but now for the normal distribution. So I'm going to ask a question again, and then we will use how to solve this problem. So the amount of money spent by students in the average, should we say average? No, just the amount. The amount of money spent by students in the applied statistics class per week is known to be normally distributed with mean. What will be your average expenditure here? 1,005. Okay. This one your name is GD. 1,500 Ghana a week. It's too small, eh? You see. It's too small. You see, they will say, you can't even buy hair. Oh, some hair, isn't it?
Yeah.
Okay, so 1,500, the average is 1,500, and the standard deviation is 30 Ghana cedis. So we are saying that the amount of money spent by students in the applied statistics class is known to be normally distributed with a mean or an average of 1,500 Ghana cedis and a standard deviation of 30 Ghana cedis. Okay. Now, A. What is the probability? What is the probability that a student selected from this class will spend up to 1,200? Don't worry, the next question will be above. Yes, up to 1,200. You see, you should have said 15,000. You see, someone. Okay, up to 1,200. Okay, then B. The B will be that above 1,800. So I should have given a general one then. Otherwise, you'll be writing. So let's above 800. We know that it will be the expenditure will be about 1,800. What else can we find? Okay, so let's do this. When we finish, we'll now generate observations, an average, observation, then we find the average and we go through the same exercise we did. So how can we find the first one?
So, do P by norm. P norm, sir.
Okay, so the normal distribution, we use norm. So if it is P, it will be P norm. If it is Q, Q norm, and so forth. So now the normal distribution. So essentially, if X is the expenditure, then what we are saying that X is normally distributed with mean what? 1,500. And then 30 squared. Remember, this will be variance, right?
Yes.
Yeah, so it has to be 30 squared, which is 900. Okay, so now the first one, remember we said, let's say R norm. So the normal distribution will have a D norm, P norm, Q norm, R norm. This distribution has two parameters, mean and what? Standard deviation. Okay. So the first question, what do we want to find? The probability that the student spends, which means X is what? Less than or equal to 1,200. If you remember this one, we can also use the tables, the standard normal tables to find it. Which means we will transform this to what? A standard normal, and then we read it from tables. We are going to do that as well to see. But we can also use, what can we use to solve this straight away? Which one? Yes. P norm. Okay. So what are we trying to find here? What name do we give to this? No. This is the CDF, exactly. So we are finding up to a number. Okay. So it means P, in which case lower the tail will be what? True, good. Okay. So let's copy P. So let's copy P norm, and then we come and put over here. It's quite long, so we can break it and bring some down. So what will be our kill or our quantile? 1,200, good. What about the mean? 1,500. What about the standard deviation? 30. Lower the tail is true. This one we can take it off. So we look at it is almost 0. 0.0023 of the yeah, so that's 300 cities away. Then the other one will also be very small. So that was A. Then what will be B? Let me. B is what? One, yeah. So that will be a very negligible probability because it's far off. To be at the long tail, you have to go into the tail. Okay. So let's see. So copy the same. The only thing we are changing is this 2008, and lower the tail will be all false. So it's almost giving us the same. Let's do 1006, which is closer. So even that is up to what? About 4 decimal places before you get a number. Let's check 550. Yeah, so we can check 510. So you can play around it. Do you get what? So small. It's because the normal distribution, it will be around it. So we are going far off. So what is happening is this. We have something like this. So this is our 1,500 mean. Okay. So if 1,200 is somewhere here. So we are looking for the area here, which is quite small. And the 1,800 is also somewhere here. So you see the area is very small, almost negligible. But if we come to, let's say, 1,510, it's closer here. So the area we are looking for, was it, so here. Yeah, so that's why. Yeah. So that's what is happening. Okay. I think we should take a break, some 5 minutes.
Thank you, Prof.
And then we'll refresh ourselves.
We don't take 10 minutes.
You want that?
15.
Oh. You don't want to go home early?
Because you normally free. It's like.
And it's like,
Why is he a pastor?
I'm supposing you, I'm lying.
Let's 10
come. Made for a crime, you was someone saying. It's one thing.
You are jealous. Jealous girlfriend. Jealous girlfriend. Jealous girlfriend.
Oh, I never knew it.
What?
I don't know.
So I realized that was why I started telling you that. No, that is the time.
She opened it over the floor, 1,000. We sound school open to the flower. And now she go there, she just see $2. She go there, hey, now how many dollars do you work on the farm? She ran there till she get her.
We need Brian.
It's my scalp.
Then you not sign.
Oh, sorry. Let me say
Small question, you know.
sorry, I even said it to Leslie.
Thank you.
That's why I can say, remember family, you want to go No one has bought it. I don't know.
Always buy 2 bottles of water. You have never seen cosplay before. One cool, one hot.
Yeah, every time I'm doing it. Yeah, they didn't me. I didn't know it's a good one because I want to charge mine. Who's are you? Why did it? Because I'm just about it. They are now charging. They've been waiting. I should have 20%. I thought socket to Mahasi.
You are coming to charge. You are coming to charge.
Everyone wants
every table one. Anyhow you be swapping regardless if your laptop is dead stop. You have to swap. You have to swap. Let me see if the laptop is dead stop.
Don't try.
No, I'll not off it to this man.
Remove our man to go.
I've not said dog say space back.
There is no, it's here. No. Somebody is charging phone here. Phone charger is here. Anyway. No. Somebody.
The thing was charging for him.
Who?
The boy here.
It's for him.
Yeah, it was for him.
About you.
So what I took it, and I said I was going to take it to the baby.
What you were saying that I wanted to say that, oh, it's for him, because I know he always carry.
It is an issue. When I got up and I said,
You were
if I'm not seeing the one for today, I'm taking to the bin. Then he said, it is for me. I'm like, ah.
Oh, space back where you saw. Now we find it there back.
I asked so many times, you didn't see anything. When I got up, it just worked for me. Like, ow.
When they come.
So this you can use this side.
When they come. Then make my party photographer. The time they come to Ghana, he say for the airports there, if they want somebody making do video for them, that will come as they are coming, that kind of video they are playing, everything, and like all the thing. Then another person you want I forgot register them both. My sister don't even buy the book. So the girls say go to they want at the time for my party, if you take them around, get come with your mother and you see. So if you rather you go chop with them.
Because you're just going to
Where you buy the diamonds? I'll give you money next time you are
I'll take him later.
They don't shop from a person like that.
I bought 2 of them. I'll take them.
Bastard. Benita. Good evening. Okay, you have to go back.
When your senses are it's a very
Can we start? Okay. So now we've seen the probabilities. Now let's see. You remember the quantiles? Which of the quantiles do you remember easily? The ones you were reading from the tables. 1.96. Okay, so now let's see. And what probability gives us the 1.96? Yes. 1.96. Which probability gives us that? 95% of what? 0.05. Are you sure? 0.05. So 0.025. Okay. Okay. So we can also use how to compute all that instead of going through the tables to do so. So that we have to use what? The quantile function, which is Q norm, right? Okay, so let's do that. Let's copy and paste. Now, so P, remember, if you do this, if your alpha is 0.05, you are going to share it on each side, right? So you have to divide by 2. So you get 0.025 and 0.025. Which means your P, if you put 0.025 here, and remember if 0 is at the middle, then on the left hand side you are going to get a negative. Remember you get negative 1.96. and also positive 1.96 at the other side. Okay, so the mean is 0. Standard deviation will be 1 because it's standard normal. Lower dot tail is true. If it's true, we are going to get the negative side. Is that okay? Because it's at the lower tail. Okay, log P, we don't need that, so we can take it off. So let's run this, and that is what you have been reading from normal tables. Is everybody okay? Now I can get a 1.96 by subtracting this from 1, the 0.025 from 1. Okay, or alternatively, I can also get it by setting lower dot tail to be false. Then it goes to the other side. Yeah, so 2 ways. If you want to get a positive side, we can change this to false, and we'll get a positive, or we can also use this but rather change the P to what? 0.975. If it's 975, then it's going to read all the way from negative up to what? That point on the right hand side. So there we have it like this. So this is what you've been reading from. What other one do you remember? When alpha is 10, you get 1.645. Yeah, so in that case, we are going to do 0.95 or 0.05. So let's try that and see. And you see, I'm not really typing all of them. I just copy and paste and change in between. So 0.95. This should give us a positive 1.645. This is what you see in the books as 1.645. So we're going to now simulate observations from the normal distribution, get a histogram for it, find the mean, find the standard deviation or the variance of it. And then we are going to fit a density curve to this function. Okay. Can we generate observations? I want you to generate now some expenditure from 20 people in this class. From what we have done, you now have the normal distribution. How would you? Remember, we have given the distribution of the expenditure. We said the mean is what? 1,500. Yeah. Are you done? Okay. What are some of your numbers? 1,500. Okay. Let's do a histogram of it. So let's do a histogram of it. So now we generate observations. So we said 20, so we start with. So I call it expenses. So in this case, you do R norm, then N is equal to 20, mean is equal to 1,500, SD is equal to 30. So mine is this. When you finish, find the mean. Find the mean and the standard deviation. So 1,000, quite close, right? And then standard deviation is SD. Or maybe we should start from 10. 34. The standard deviation was 30. So let me start from 10. So you see it's far off. Then I increase it to, I'm left with the histogram. So hist expenses mean is equal to that. So let's see. So this doesn't look like a normal distribution. Okay, so I increase it to 100. The mean is getting closer to 1,500. The standard deviation is almost 30 as well. The histogram is now approaching normal a bit. So I can increase it to 1,000. I expect more improvement in both the mean, you see, and the standard deviation. And the histogram is actually approaching normal and so forth. So 10,000. Yeah. Is everybody okay with what is going on? Okay, good. Now, what we need to do now is that now we know how to generate observations from a distribution and so forth. Okay. Yes. Yeah, we'll get there. So, first of all, so now we know how to generate observations. But how well, you see, we are using the frequency histogram to help us check the distribution. And we realize that when the sample size is small, you don't really get the shape of the distribution well. So even if it's normal, you still have, it doesn't really approach normality. As the sample size increases, whether it's exponential or whatever, you tend to see what really is happening. There are so many distributions. There is the T. Remember, you were using normal and T. We can also get a T. T is just small t. So you have QT, you have PT, and then you have what? RT, and you have also DT, and so forth. Chi, we have R chi, Q chi, P chi, and D chi, and so forth. So all those. F as well, DF, and so forth. Okay. So now, we want to now check if a distribution fits a data. What are some of the descriptive statistics you can use to check whether a data fits a particular distribution? Okay. So to do that, we have what we call quantile plot. Have you heard of it before? Quantile plot, or QQ plot, more popular. So for example, what we have done in normal is called QQ norm. So if I do QQ norm expenses, I get this. What is actually happening is that, please, you know what order statistics is? Order statistics. It's a statistics in order, right? That's what they say, you are begging the question. You are using the same question to answer. Yes. Okay. So essentially, you know, order statistics is when you have a data set and you order it, we say you have created an order statistics. So the ordering may be from the minimum value to the maximum, or it may be from the maximum value to the minimum value. Now it turns out that we can always generate other statistics from the distribution, and then we place it along with your data. So we have the actual, you see the theoretical quantiles is the quantiles we get from the normal distribution. Then the sample quantiles is the order statistics. So if they obey that line, if they are, it follows that particular distribution, we expect a straight line passing through the origin and also have 45 degrees as an angle. So if you look at it, this is very close to normal. And it's no coincidence because we simulated the data from where? A normal distribution. Is that okay? Now, let's look at KOKO norm, but let's take the times. Do you remember the times? That one is from where? Exponential. Good. So let's see whether it takes a bit of time because that's quite a lot of data. I think it hasn't shown. You see what is happening? So what this is showing us is that the data does not follow normal. You see the curve is like that. Okay. So it doesn't really fit. So if you draw a line, it is possible that the line will be somewhere here. The values will not be on it. But if you compare this with the one we got from here, it will be a straight line passing through the origin. So in this case, yes. In yours, it takes a bit of time to come. If the data set is large, remember the last one was like 10,000. So yeah, it has to order all the 10,000 and also calculate the theoretical quantile. Okay. So we can use this concept to, before you go to what you did in the inferential statistics, this is what you do. So if the normal distribution is not a candidate distribution for my data, I don't even start with it at all. Is everybody okay with this? Please, are you okay?
Yes.
Yeah, okay. So we are going to study this quanta plus some other distributions. So let's all install the package called REINS. Yes, R-E. I don't even have it as well. Okay, so let's install REINS. It's reinsurance. REINS, like this. REINS. So install. Good, okay. Then there's also, let's also install insurance data. So REINS. You remember the car price? What we did yesterday. Let's look at a histogram of it and see how.
The second package.
Yeah, insurance data. When you finish, let's take mass. So cars 93. let's check the price. Okay. So will you advocate that we use a normal distribution for this? What distribution would you prefer for this? Between exponential and normal, which one would you prefer?
Exponential.
Exponential. Okay, so that's the sort of, so we need to check. So we can use the QQ norm, but the exponential one, we have to take it from the RAINS package. Okay, so let's see. So if you have installed it, make sure you take mass and also you take RAINS. Okay, like that. Okay. Let's check. So let's do QQ norm. CAS 93 price. Okay. So this one, for us to be able to get it, we can even put them side by side. And then we'll be able to judge which one is better. Okay. Now there's also ESPQQ. This will also plot an exponential quantile plot. So we can also put this one in there. And that gives us this. So between this and that one, which one is better? Remember, the criteria is that they should fall along the line, and the line should be within the 45. It should have 45 degrees. So between this, I can also get all of them on the same graph by using what? MF rule, right? See, 1 row, 2 columns. Okay, so now you can actually check. And this is the more reason why I don't like the top, the main. So all this, we can put main is equal to empty, and then we won't have any. So let's do it again. There, and it looks nice on that. This is also one aspect of statistics that you need to take note. You see, there is a book called Using Statistics to Lie. To lie.
Lie.
Yes. So, you see, if because of the way I've chosen, I chose the x-axis, it can put everything together and then it looks like a line, a straight line. Is that okay? Yeah. So if I pop this out, you tend to see it better. Okay, so now you realize that the exponential is doing a better job than what? The normal. Okay. I'm going to add another distribution. The other distribution is called Pareto, and we can get it. So let's look for Pareto as well. That is also Pareto QQ. So they are all in the, what do we call it? The re-ins package. So let's get the Pareto QQ plot. And then I'm going to put all of them side by side. So now I'll change my 2 to 3 so that I have all of them on the same graph. Okay. So I can pop it out. The only thing I did was Pareto QQ. And then I copy the rest and put it in there. So let's see. I think the exponential is still better. So we can go on and on and on and on. Log normal, Weibo, QQ, and all those. Yes.
Right now, I'm using eyeball.
Yeah.
Can we draw an AB line?
You can. We can. But it means you have to fit a regression later on. Any question? Oh, it's the same thing. Pareto. Okay. The arguments are the same. They have also log normal. I think L norm.
Normal QQ.
As what? Okay, let me say normal. It's capital. Capital L.
It's log normal.
Okay, so it's up there. Yeah, so this one, that's also log normal. There's even Weibo, I think. So this one looks a bit promising. There's also Weibo QQ. So I can try, how many do I have now? 1, 2, 3, 4, 5. Okay, so now I'm going to do 2 by 3, which means I have 2 rows and what? 3 columns. I'm left with 1. So you can pop this one out and then look at it. So this is how you get what we call a panel plot. So in all this, the candidate models will be Pareto and what? And exponential. And they are actually related. If you have an exponential distribution and you take log of it, you get an Pareto. So look at it. I think the Pareto seems to be the best, followed by the exponential. The rest is difficult to choose. Which one? Okay, so let me get out of this. You can also do it like this and see those things. So those that will be maybe in your thesis and so forth, or the project work that you are going to do. These are some of the things if you are fitting a distribution, you start with. And then you talk about the fits and so forth. So we need to be able to ascertain that the distribution fits it before we now go into to select the model and start doing estimation itself. We will get there to how to do estimation later on. So next week, I think next week, Dr. Isa will be meeting you. So the following week, please, you need to revise your estimation notes. The way you do estimation, moment, maximum likelihood, we are going to implement them in our. So here, you read that we have not estimated any parameter. So soon, by next week when we meet, we'll be able to estimate if it's exponential, find the best parameter estimate for it. In this case, we find the rate, and then we can now superimpose the curve, the exponential curve, on the density plot. So. Okay. Yeah. It's because you don't have enough space. Increase the space of the graph space. Yes. Yes.
The Pareto seems to be the least.
Yes, if you look at it, it shows a bit of. But remember, okay, yeah, this one we have the same data, so we should have the same result. If you look at it, the Pareto seems to have a straight line. No, that's the bottom left. Log. It's log normal. No. Okay, yeah, it's true, yeah. So standard normal. Okay, so it's a log normal rather. Thank you. I did not check because I saw log x. The distribution based on logs, they perform really well, mostly. Okay. What else do I want to talk about? Sorry. Yes.
I think the Pareto and the exponential exponential.
Yes.
The x-axis are both labeled quantiles of standard exponential.
Yes. That's why I said if a random variable is exponential and you find the log of it, it becomes a Pareto. So they are all related to the exponential, standard exponential random variable. It's the same as the normal. Look at the normal. They all, log normal and log normal, they all relate to the standard normal. So that's how they are. Okay. Now, if you look at the course outline, there was what we call inverse probability transfer. So let me end with that. Okay. This is applied statistics, so we don't want to do any. But remember that today we found the exponential QQ, right? You remember? The the quanta of the exponential distribution. Okay, now look at it. For us to be able to find the quanta what did we do? We found the inverse, right? Or we inverted this function. In math, that's the same as applying the inverse function of p. And if you apply inverse of this will no more be there. So you will be left with x is equal to f inverse of p. Is that okay? Now, it turns out that this is also probability, right? If you remember, I said SHS, you do 0 to 100%. 50% will be the, so if you cannot, it can also be 0 to 1. So this cumulative distribution function is also a probability. Is everybody okay with that?
Yes.
Good. Okay. So, if I want to generate any distribution and I know it's CDF, I can generate it from the uniform 1 distribution. The uniform 0, 1, you remember the uniform distribution? It's rectangular. Right? So the uniform 0, 1 is a probability distribution. Okay. What are we saying? Well, it means that if I want to simulate observations from an exponential, instead of simulating it from that RSP, which is the exponential, I can also simulate the observation from a uniform distribution and transform it into Pareto. And we do so because of this principle, which is called the inverse probability transform. Or transformation, transform. Everybody okay? Now, why is this important? Well, it turns out that it's not every distribution you find in, let's say, R. Okay, so if we come up with a distribution today, you cannot have a package in R that will implement that distribution. So the ones we are doing now, we are lucky because somebody sat down to write the codes for us. But we realized that we can also write our own code to reproduce whatever is in R. That's why in R it is important that you know how to write functions. If you know that and you know the mathematics behind whatever, you can program it yourself. Okay. So this principle helps us to generate observations from every distribution, because once we get the inverse, this one will be any number between 0 and 1. If you pass it through here, you get the x. Okay. So you wrote a function for your quantile function, right? For the exponential. Isn't it? You did? Right, okay. Remember you were putting in a probability, then you generate the y, right? The quantile. Okay. It's the same principle we are going to use. So that P you are sending in is like an observation from a uniform distribution. Please, you know what I'm saying? The uniform distribution is like this, or because it's getting to 8 o'clock. Okay. So it's like that, right? They are distributed over here. So that's a standard uniform. So whatever you did, it's like you pick one observation from here, you put it inside, and then you generate the exponential. So what we are going to do is that now, if I ask you to now generate observation from exponential distribution, instead of going to use RSP, we can actually use our quantile function we wrote to now generate the observation. And let's do that, and then we can close. Please, is everybody okay with the concept? Okay, all right, so let's see. So we go back and talk about inverse probability transfer. I can ask you this in your exam. In fact, I'll ask you.
Is it transform or transformation?
It's transforming, so, but it's the same transformation. So let's go and get it was Q ESP or something. It was this function, right? This. So remember, we said I don't need to repeat it. We said our lambda was 5 minutes, right? So I am going to use this to generate 10 numbers from the exponential distribution and so forth. Now, how do I do this? Well, what I'm going to do is to just do an example, but I'll go into the function and change it. But let's see. So let's call it p hat. So p dot hat, it means we will take our sample from a uniform distribution. That uniform distribution should have n, let's say 10. Min is 0 and then max is what? 1. That's a uniform. So this one, every number you generate from it will be between 0 and 1. Okay. Now, if we put this through this function, we should get an exponential random variable. So do you get what I'm saying? We want to generate exponential. We go through two routes. We generate from a uniform, and then we use a function to transform the uniform probability into what? An exponential random variable. So what we are going to do is this. Now, if I take this Q-fan and I say P is equal to P dot hat, and then lambda is equal to 1 over 5, yeah. Then whatever, what did I do? P is equal to P. Yeah. Whatever I get will be exponential random variable. Okay, and if I let's say I call it T times or trial times, then anytime I plot this, you realize that it will follow the exponential, just so you see. So let me clear this so that we come back to our single. I need to do PAMA again. I need to change the margins. Okay. So we can go back if we want to. So the same thing we did previously. Let me even put the mean there just to show us whether our mean is getting to the 5 that we want. So it's 5.210. Let's increase it to 100. 5.19. So it's getting closer to exponential. What else? We change it to 1,000. See, it's getting closer. So what did we start with? We started with uniform distribution or probabilities. But we end up generating what? Exponential. The curve is not like the distribution of the exponential I have over there. Is it a rectangular in shape? No. It follows what? An exponential. And we have demonstrated that it is actually giving you the mean, which is equal to 5. As we continue increasing it, the sample size, we even get closer to 5 as much as possible, 4.99, and it shows that it's actually following exponential. Yes.
Please, how do you get rid of the thing?
Okay, so you can clear your plot, but if you want it to stay, then you can also come to Parma and then par MF row, then C11, which means 1 row, 1 column. Yeah. Okay. So that is it. Now, using this principle, we can generate observation from any distribution, including those that are not in R. And one of your projects will be to do some of these things. When we give you a distribution that you cannot find in R. So if you can't find the distribution, all you have to do is to go through what we have done. So in other words, you invert it, then you generate observations from a uniform distribution, and then you pass it through that function, and then you get observations from that. There's even a more complicated one where the CDF cannot be inverted. If the CDF cannot be inverted, what do? We resort to a numerical method. In other words, we will send the P to the other side so that we have an equation, f of x minus P is equal to 0. So we turn this into a numerical problem where we are solving for the zeros of that function. And each time we do so, we get a new random variate from that distribution. And I'll show you some of them in some of the works we've done. When we meet, I'll show you a sample from real data, a paper that I'll give to you to review. Okay, any question? I think it will be enough tonight. Maybe we should get another class that will continue to 10. Yes, I think we have to apply to the government that we want to run statistics 24 hours. In the next election, they will say, "Oh, we have implemented 24 hours." Then we also run shifted.
So what's the topic for this one?
This one. So what we are doing is there's an inverse probability transform. Yeah, but they all fall under generating observations from distributions. So I'll send you I'll put the codes in the